Sorry about that, everybody. I got cut off in the middle of a lecture. Believe it or not, the video was interrupted by a pop-up. Oh my goodness. Well, anyway, back to business. We're talking about theoretical probability now. I haven't mentioned that word yet, but I'm about to. We need some definitions and concepts first. If every outcome of an experiment has the same chance of occurring as every other outcome, then we say that the outcomes are equally likely. Here's an example. We toss a coin once. We have two outcomes, heads and tails. And each one has the same chance of occurring. So heads and tails are called equally likely outcomes. Here's another example. We take a single die, one dice, we toss it once. The possible outcomes are 1, 2, 3, 4, 5, 6. And each of these outcomes has the same chance of occurring as every other. We have just as much of a chance of getting 1 as we have getting a 5. The chances of getting 3 and getting 4 are the same. So all of these outcomes, 1, 2, 3, 4, 5, 6, are equally likely. Here's how the concept of equally likely relates to probability. If an experiment has n possible outcomes, and all outcomes are equally likely, comma, then the probability of any one outcome occurring is 1 over n. For example, we toss a coin once. There are two outcomes, heads and tails. They're equally likely. So the probability of either of these two outcomes occurring is 1 over the total number of outcomes. If all outcomes are equally likely, then the probability of any one outcome occurring is 1 over the total number of outcomes. So here we have two outcomes, heads and tails. The probability of either one occurring is 1 over the total number of outcomes, too. Another example, we toss a single die once. There are 6 outcomes. We can either get a 1, a 2, a 3, a 4, a 5, or a 6. And these outcomes are equally likely. So the probability that we get any one of these outcomes, for example, a 1, is 1 over 6, 1 over the number of possible outcomes. The same with the probability of getting a 2, 1 over 6, 1 over the total number of outcomes. So the probability of any one of these outcomes is 1 over 6, 1 over the total number of outcomes. Okay, here's why equally likely outcomes matter. Given an experiment with n equally likely outcomes, the theoretical probability of an event occurring, an event which we're going to call E, the theoretical probability of an event E occurring is given by probability that E occurs. It's going to be the number of outcomes that result in E occurring over the total number of outcomes. So the probability that the event E occurs is the total number of outcomes that result in E occurring over the total number of outcomes, period. For example, our experiment is that we toss a single die once. So the equally likely outcomes are 1, 2, 3, 4, 5, 6. Let E be the event that we get a 4 or greater. So in other words, we either get a 4, we get a 5, or we get a 6. The probability that E occurs, that is, that we get a 4 or greater, is the number of outcomes that result in E divided by the total number of outcomes. Now we're tossing a die, so the total number of outcomes is 6. Of those 6 outcomes, the total number of outcomes that result in E is 3. But we either get a 4, we get a 5, or we get a 6. So the probability of getting a 4 or greater is 1/2. Oh, let's do another theoretical probability exercise. Our experiment consists of drawing a single card from a deck of 52 playing cards. So there are 52 equally likely outcomes. Each of these cards, when drawn, constitutes one of those 52 equally likely outcomes. Now let E1 be the event of drawing a heart. So the probability of E1 occurring is number of outcomes resulting in E1 over the total number of outcomes the total number of outcomes, 52. There are 52 different cards that we can draw, so drawing each of those cards is an outcome. 52 different outcomes. Now, the number of outcomes that result in E1, drawing a heart. Well, let's see. We can get the 2 of hearts, the 3 of hearts, the 4 of hearts, the 5 of hearts, the 6 of hearts, the 7 of hearts, the 8 of hearts, the 9 of hearts, the 10 of hearts. We can get Jack, Queen, King, Ace. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 13 different outcomes that result in getting a heart. And when we reduce this, the probability of getting a heart turns out to be 1/4, which doesn't surprise us. There are 4 suits of cards: hearts, diamonds, spades, clubs. So the probability of drawing a heart we would expect would be 1 out of 4. Now let's look at E2, the probability of getting a 6. Or the event of getting a 6. This probability is the number of outcomes resulting in E1, in E2, that is the number of outcomes that result in a 6, over the total number of outcomes. The total number of outcomes, again, that's 52. There are 52 different cards that we could draw. Now, the number of outcomes that result in getting an E2, that result in getting a 6. Well, we can either get the 6 of clubs. Is that what that is? No, that's a spade, isn't it? We can get the 6 of clubs. We can get the 6 of diamonds. We can get the 6 of hearts. Or we can get the 6 of spades. So 4 different ways that we can get a 6. which means the probability of drawing a 6 is going to be 4 out of 52 or 1/13. Some more facts about theoretical probability. If an event E cannot occur, then the probability of E occurring is 0. So maybe an example of this is that E is the event that I throw a ball at the ground and I miss. The probability of that event is 0. Now, if E is an event that must occur, then the probability of E occurring is 1. Maybe we could say that E is the event that I throw a ball at the ground and I hit it. Well, the probability that I throw a ball at the ground and I hit the ground is going to be 1. It has to happen. Let's see. I'm at a loss for a better illustration. I'm sorry. For any event, the probability that the event occurs is between 0 and 1. And I guess that makes sense because, especially if we're looking at equally likely outcomes, the probability of an event occurring is the number of equally likely outcomes resulting in E over the total number of outcomes the number of equally likely outcomes that result in E can't be any less than 0. So the smallest that this could be is 0 over the total number of outcomes, which is 0. And the number of equally likely outcomes that result in E can't be any greater than the total number of outcomes. So the largest that the numerator can be is the same as the denominator. So the probability of any event E occurring is between 0 and 1. The sum of the probabilities of all outcomes of an experiment is 1. And this is a biggie. The probability that E occurs plus the probability that E doesn't occur is 1. And that makes sense. Given any event E, one of two things has to happen. Either E occurs or it doesn't occur. So these are the only possible outcomes. The sum of these probabilities is 1. And from this, we can rewrite the equation. It's sometimes helpful to compute the probability that an event occurs by computing 1 minus the probability that the event doesn't occur. Sometimes this is a helpful relationship. Now let's look at a few more examples. Let's look at an example that illustrates number 4. The sum of the probabilities of all outcomes of an experiment equals 1. And for that, let's look at the experiment. We roll a single die. The outcomes are that we get a 1, we get a 2, we get a 3, we get a 4, we get a 5, we get a 6. Those are all of the outcomes. These are equally likely outcomes. So the probability that we get a 1 is 1 over 6. The probability that we get a 2 is 1 over 6. The probability that we get a 3 is 1 over 6. The probability that we get a 4 is 1 over 6. The probability that we get a 5 is 1 over 6. And the probability that we get a 6 is 1 over 6. So what's the sum of the probabilities here? If we take the sum of the probabilities of each of these outcomes, we're going to get 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 6 times. Probability that 1 occurs, probability that 2 occurs, probability that 3 occurs, 4 occurs, 5 occurs, 6 occurs. So the sum of all of the sum of the probabilities of all of the outcomes of an experiment is 1. Now let's consider an example that may show the value of this relationship. Okay, our experiment again is that we toss a single die, and E is the event that we either get a 1 or we get a 2 or we get a 3 or we get a 4 or we get a 5. So that means probability that we get a 1 plus probability that we get a 2 plus probability that we get a 3 plus probability that we get a 4 plus probability that we get a 5. And that's 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6. 5 of these things. Probability that we get a 1, probability that we get a 2, probability that we get a 3, a 4, a 5. So this is 5/6. Well, there is an easier way. The probability of E occurring is equal to 1 minus the probability that E doesn't occur. And what's the only way that E cannot occur? The only way that E cannot occur is if we roll the die and none of these 5 things happen. Well, if we don't get a 1, we don't get a 2, we don't get a 3, we don't get a 4, and we don't get a 5, what has to happen? We get a 6, right? So this is 1 minus the probability of getting a 6th. And the probability of getting a 6th is 1/6. And so that means the probability of E occurring is 5/6. It was easier to do it this way. And as we get deeper into probability, this kind of trick, the probability that an event occurs is 1 minus the probability that it doesn't occur. This trick is going to be very handy at times.